Okay. And in your terminal, you'll want to open a shell. So click on that and then tab. And then you can type in IPcluster start -n, and then some number. I'll suggest 2 or 3. Any more than that would be a little crazy. But what we're going to do is we're going to just start IPcluster locally on your Wakari session, so you won't have the visceral thrill of sending this over the interwebs to Amazon, but you'll still be able to run all the commands basically unmodified and see how it works. So once you execute that, so IPcluster start -n3, it'll give you some output like this. I have it started up already. And then you would modify your notebook. Instead of that really long client equals client line, you would just modify it instead to be this really simple one. So client equals client parentheses. Right, and then if you go ahead and do that, this one is running locally now, and everything should work. Yeah. Oh, the IPcluster command? Yes. Okay. Does everybody have something? Okay. All right. Let's do some things. Okay. So hopefully everybody's got something and had a chance to go through this a little bit. So I wanted to point out a couple important parts that got lost a little bit in the chaos. Number one is that this first set, this resp equals direct.apply. When we do just resp, we're getting an async result, and then we have to .get it, and that's because that's a non-blocking call. Right? So we sent off the command, we're not waiting for any output, and we have to get that output manually. We need to ask for it later. And this is nice because you could send off some statistical job and then start cleaning your data for your next job and then get it when it's done. Right? But sometimes we want to know right away when that stuff gets done. So you can set this option on the view. That's this direct.block equals true option. And the exact same 3 commands, these next 3 lines are exactly the same as the ones above. They give you a little bit different output, right? Resp now is a list of the outputs. Oh, I have to. Right, so I set it to blocking. Obviously, it doesn't block for very long. Return hello does not take very much CPU time. Resp gives me a list now, and there's no get method because it's not an asynchronous call. There's nothing to get. It's just a list. Okay, so this error was on purpose. That is authored in there. Okay, hence this note. Note the different behavior. All right. Questions? Yes. Yes. Yeah. So there's other ways to poll and see if something's running, and so you'd wait, and then you'd get all the results. You'd gather them all up. Okay. Questions? Okay. So that's cool, but that's not a very interesting thing to do on these other nodes, right? So we want. These other nodes are running in their own namespaces, right? Which is good because we might have a lot of data here on our local machine. We might want to, munge all this data and do a bunch of awesome SQL stuff and outer joins and whatever locally, and then push little pieces of data in aggregate. So the sharing of data between the between the namespaces is manual. So if I declare a variable here, this a equals 4, and we define this function square, this direct is our view, and then the push method lets us push those into the remote namespaces. Right? We have to use this sort of dictionary notation, and we give them names for our objects because it can't read, basically. So it's hard to remember sometimes, but you need to have the name of the variable and then actually the variable or the function or whatever the object is. Yes. Yes. But it's ugly, and I'm pretty, and so I don't want that on my. I don't need that on my output. And then once we have that, we can go ahead and just execute evaluable strings on the remote objects. And we've got this b equals square a, so we know this b object is going to have some result in it, and it's using both the function and the variable that we pushed. And now we know that's in the remote namespace. We can analogously pull it back to our local one, and here we go. We've got 3/16. That's awesome. I'm very glad I have Python to tell me that 4 squared is 16. Okay, so now I say try out the following, which probably means I'm trying to get you to do something bad, which I do. There's an error. Right, so I import date time, and I have a method that just prints out the time now. And just like I did before, I pushed my function, and then I tried to execute it remotely, and I got a bunch of stack traces. I got 3 of them because there's 3 remote nodes. Date time's not defined. What's the deal? I imported it right here. Will somebody please tell me what the deal is? Right, separate namespaces. Right, so there's 2 ways to remedy this situation. The pretty way, which I'm into, is this context manager here, so direct.sync imports. If we do that, if you do your imports in a sync imports context manager, it'll import it both on my local namespace and on the remote ones, so we can make sure that we all have the same imports going on and we don't deal with those issues. And then we can go ahead and do the function that we wanted to in the first place. Right? And since I know somebody's going to ask, yes, execute will run anything you want to eval, including an import. So you could just put all your imports in the actual strings to go ahead and eval and do them like that. And it'll work happily. It'll import it in the remote namespaces. But then you might run into the opposite issue. We have things imported remotely but not locally, and you don't want that. So use context managers because Guido put them there, and you should use them. Questions at this point? Are we excited? Are we members of the 21st Century Concurrent Programming Club? All right, great. Yes?
I tried to execute print statement and that return. Can I get at that, or is that lost?
I am 95% sure there's a way to get at the standard in on that remote node, but I don't remember right now. I would avoid doing that as much as possible. Partially because of style. Like we're trying to work in this sort of like functional paradigm when using apply and these maps and stuff like that, and relying on print statements is like relying on side effects. And partially because if we want to do anything with like real asynchronicity, we can't rely on stuff like that. Okay, so I don't know what Daft Punk has to do with that demo, but I was listening to them when I was doing this. Okay, so how are we going to use this? All right, we needed a use case that fit my guidelines I said before. We need something cool but embarrassingly parallel, but mostly cool. And so my use case is Bayesian estimation, because that's something I know. Right? This is a nice plot here. We've got knowledge of Bayesian data analysis as our independent variable, and your happiness and success as the dependent variable. As you can see, they're directly correlated. This is all from John Krischke's infamous puppy book. I encourage you to check it out if this part of this talk appeals at all to you, because it's awesome. It's the one with puppies on the cover. Right, so okay, so we have some data, and there might be some relationship here, right? And plotted here are credible regression lines. If you looked at this, these are all pretty reasonable. They're within, reasonableness. And what we want is, we would like the probability distribution for any such line that you wanted to put there. We want to know about how credible that line would be to fit that data. Right? So we want the full probability distribution of our output, right? So what does a line look like? It's that beta naught plus beta 1 x1. I promise this is the only math here. It's really not that bad. You can just look at the pictures and pretend I'm not talking about Greek letters if you want. Right, so we've got y equals mx plus b basically. But what we're doing is we're putting a probability distribution on each piece of the parameter space we're looking for, and the parameter space being the intercepted slope of this line. Right? So we're putting normal distributions on these betas here, and those are our priors. We say we believe that these parameters are normally distributed, and our data, this yi at the bottom, which would be the actual dots here, we're saying those are also normally distributed, and the parameters for that normal distribution are that line that gives the middle of that normal distribution and the width. So it's tau here, but it's just it's the inverse of standard deviation, and that tau is given by a gamma distribution. If you don't care about why, you don't need to care about why we picked those, but just the fact is we put probability distributions on all of these things so that we could get the probability of any of these lines matching this data. Okay, why do we care, right? So this is nice because once we build such a distribution, we need to we want to use Bayes' theorem to actually get the probability of any of those parameter sets being the ones that have generated that data. And in order to do that, we can use multi-chain Monte Carlo sampling. Right? The nice part about MCMC sampling is we're using it to evaluate this really intractable integral. Well, it's usually intractable. But if we look at this, what this is, it's just a schematic of a Monte Carlo integral here. And what we're doing is integrating the area of this circle. And all this process is doing is we're throwing darts repeatedly at this circle. And we know the shape of this circle. We don't know how much is inside. And when we throw darts repeatedly, we're just asking, is this inside the circle? It's blue. Is it outside the circle? It's red, right? And so we do this over and over and over, and if we count and compare the number of blue versus red, we get a good estimate for the area of this circle. The more darts we throw, the better that estimate's going to be, so the better our estimates of these parameters are going to be. The nice part about it is it doesn't matter when we're throwing darts at this if it's just me throwing darts at it or if everybody in this room is throwing darts at this. All that matters is that at the end, I have the right count of how many darts are in the red area, how many darts are in the blue area. This is an embarrassingly parallel problem because we can farm this out to as many nodes as we want to throw darts at this probability distribution and figure out which things are underneath the probability distribution and which things are not. Okay, after attempting that, this is my neon. I wish it was. We're going to look at the notebook for how we go about doing this. So if you open up this hot hand parallel notebook, there's some exposition there. I wrote it, but writing code is more my strong suit than my exposition, so you can listen to me talk instead. So what we're going to investigate here is of much debate from where I'm from. Right? So I come from Indiana, and there basketball is less of a sport, more of a religion. And one of the religious debates that frequently occurs is whether or not the hot hand effect exists. Now, for those of you not familiar with the beautiful game, the hot hand effect is the presumed increased likelihood of making your second free throw if you made your first free throw. The reason being, you got it dialed in, you make the shot, you just do the same thing instead of having to adjust your shot the second time. Makes sense if you go ahead and say it, but the question is really like, once you get to the pros, is that a factor anymore? Some people say yes, some people say no. I say let's write some software to find out. So here's our data. It looks like this. I've got a little bit printed out. I got a bunch of play-by-play data from the NBA. We've got game IDs, event indexes, time left, but the important part is this event here. And luckily, these events are in a very readable format, and what we care about are these pairs of free throws. We've got a player throwing one free throw, some result, player throwing a second free throw, some result. Luckily, most free throws are done in pairs, so we'll have a lot of these pairs. We need to write a little bit of code to chug through this GZ text file here. I should probably do my imports before I do this. And this just goes through and grabs all of those and counts them up, right? So we're just getting all of those events and counting up how many pairs each player has and getting the top 10 players who threw the most free throws, because they're going to give us the most interesting results. Right? We got some various people on this list that you might recognize. These James and Wade guys, they're pretty good. So I recommend comparing results for Blake Griffin and LeBron James. After you run them both, you might figure out why I recommend those two. Cool. I'm going to pick Blake Griffin because he slam dunked over IKEA once, and that was pretty awesome. Okay, so if I can figure out how to scroll on this. All right. So we're going to go through these, and we're going to look at each pair of lines in this, and we're going to say, is this a pair of free throws? And if it is, we're going to add it to a counter. And these possible outcomes are false, false, true, false, false, true, true, true. And the key here is, did you make your free throw? So a true, true is I made both of them. True, false is I made the first one, not the second one. All right, so Blake Griffin had that many. It's pretty cool. And if we, then we want to group these together, right? We want to group them by the missed first and the made first, right? Because this is our question. We want to look at the probability of making your second free throw conditioned on the outcome of your first free throw. So we group those together, and we put them in these big vectors, or lists, excuse me. Sorry, my R speak is getting the most of me. We've got a 0 for missing the second one, and a 1 for making the second one. Okay, so got our data. We want to import PyMC. Great. Really?
Yeah, I found that.
And you didn't tell me? I didn't want to. Okay, all right. Well, how amazing is Wakari? Because we can do this. This was supposed to be installed, but, we'll do it live. So I talked about bang magics and all the neat things that IPython Notebook can do for you. One of the things you can do is execute things from your normal command line in your IPython Notebook. So if I don't have PyMC, I can do this. This is probably going to destroy the cheese shop, but no? Conda pip? Oh, it is. Yes, you're right. It's in Conda, not pip. It's probably not working for me because of great. I'm really scraping the bottom of the barrel now. Right. It's been that long. Okay. Okay. Any questions at this point while we all wait for everything to install? It's preferable to use Conda install PyMC if you can. I think the pip was failing for me because I had the local cluster, IP cluster open. Did you have a question? Yeah. So multi-chain Monte Carlo. All we're saying is that the Monte Carlo part is that we're taking random walks through the parameter space, and the multi-chain means that we can run multiple chains at the same time. And the reason we're running multiple chains is because we're going to run one on each of the IP cluster nodes. Did this work? No. Right. You can't. And in fact, you also, in IPython Notebook, you can't even do like raw underscore input from Python. And that's something that they're working on fixing in the next version, whatever. It's on the roadmap.
So I just ran that too. So you like -y or some kind of yes, I would.
Probably yes.
Probably the terminal is the best place to do this.
Yes.
One of the reasons the terminal's there.
Thank you. Yeah. It would have been good if pip worked. This is fine. This is good.
So,
Yes.
do Conda install in here, we are eventually going to need this on our slave nodes also.
That's true. Yeah, we're going to. Yeah, so it might be best. Okay, all right. So it might be best if we did a conda install here, and then I guess we're not going to be able to use the remote nodes for this. And then, we could all do start the IP cluster locally, like we did for the people whose engines wouldn't start. Cool. Okay. Yeah, there's a lot of traffic on Wakar right now. Sorry if it's a little pokey. If you lose the tab, sometimes you can go to View and then Workbench to get them back, or then View Notebook and then View Workbench.
Suggestion for no environment found for Conda install.
No environment found.
No environment found.
Are you doing that in? Is that on Wakari or are you local? Okay. In the shell. We have to create an environment.
So the pip fails to the linker not finding the MKL libraries.
All right. Let's see if Conda does it. At the very least, hopefully I can show you how cool it is. We get such great graphs. It's so good. Yeah, it's more of a package manager than like Pip. Yeah. Okay, let's let's use this moment. If you're installing, please go ahead and install. If you're just waiting on Conda to finish, it's because all of us are writing to the same disks. These disk-intensive operations take a little while. So if you're just waiting, let's talk about Bayesian data analysis, because it's a passion of mine. Right, so among the things we're going to do, once we can do it, is we're going to get all this stuff. And the first plot we'll get will look like this. All right, so this is the, in those two groups of making and missing the first, we get this plot. And it comes very easily because we can just basically, this is just two histograms, really easy code if I can scroll up. We get back these traces, which are samples from the posterior probability distribution. And all we do is histogram those. There's just a couple of them, and those two correspond to the different situations. We histogram those, and we get this nice thing, right? So in a data exploration standpoint, if you saw this graph, you'd be, yeah, I'm pumped, right? There's a difference. Well, this is cool. Look, we got two different humps. They're pretty separated. These red lines are the means. They're definitely far apart. I mean, we got like 0.67 there. That's awesome. Like, let's write it up, send it home, right? But no, we're classier than that. We're Bayesians. We're going to go further. We can't just do that. Even if we were frequentists, we'd at least try a p-value, right? We try to get that, but we're not. We're Bayesians. So our strategy here is we've got two different quantities, and we've got some estimate for these two quantities. These means are basically our estimates for them, and the histograms show credible-ish values. They're just the samples from the posterior distribution. So what we want is we want some notion of the most credible values. So the frequentist analog would be the confidence interval. We're going to use what's called the highest density interval. Right? And the highest density interval is basically the shortest in terms of your sort of x here, your probability. So the shortest interval that contains 95% of the probability mass. And it's sort of the tightest bound you can put around 95% of the probability. And it represents a credible region. Right? So once we have that, we could put those around each of these if we wanted. I'm still having trouble with the scrolling. Okay, cool. But what we really care about is the difference between the two, right? Our question is, are these two quantities different? Is the probability different conditioned on the outcome of the first thing? So we can look at the difference between those two traces. Since each of these samples from the posterior probability distribution is a conjoint probability, so it's across all of the different parameters, we can just take the difference of these two samples because they're from the same random walk. They're just the different parameters, so the different dimensions in our random walk. And we want to look at the difference of that. So we can plot the difference, which looks like this. We've got our mean. This mean is some positive quantity. And when we put that HDI, the high density interval, around that quantity, we see that this HDI excludes 0. Right? So this is sort of what we would be looking for. This would be like a p less than 0.05, right? This is our confidence interval excluding 0 for the difference between the two quantities. So it seems like, at least for Blake Griffin, there is some hot hand effect that he seems to make his second free throw more than his first. Questions about that? About statistics, Bayesian, whatever, anything? That's still doing its thing? Okay. There's a lot more to it. A whole lot more to it. Yeah, so the book, the puppy book, which I refer to offhand, is called Doing Bayesian Data Analysis, right? And it's a beautiful book for data scientists because the title is what you're doing. You are doing Bayesian data analysis. There's like one integral in the whole book, and I'm pretty sure a third grader could do it. Like, it's no big deal. There's very little mathematics. It's all about getting your hands dirty. Unfortunately, it's done in R, but it's pretty easy to translate to Python. Very, very excellent book. Right? So the differences that I'm hem-hawing about have to do with the fact the assumptions that go into calculating a p-value. There are certain assumptions that go on in your experimental design that are not being made here. Right? So there's a class of people, myself among them, who say that a Bayesian HDI is strictly better than a frequentist confidence interval because there are fewer assumptions being made about your experimental design. Still working. Okay. All right. Cool. All right. Yes?
You say here that it is the smallest interval to contain 95% of the posterior
Probability mass is what I should have said, but.
yeah, I was confused. Do you have in the upper part in this graph, you have two distributions?
Yes. So I'm not putting the HDI on this. I'm putting the HDI on the distribution of the difference. So this is my one distribution, and these green lines bound the 95%. The other difference is that HDIs are not always symmetrical. So this is another difference with confidence intervals, and that's also a benefit of them, because if your distribution is skewed, why would you think that your confidence interval should be symmetrical? So the fact that they're not symmetrical is useful. Okay, so I'll continue to spoil the surprise. If we look at the actual sample in our parameter space, right, there's two parameters, and that was the probability of making the first free throw if you missed the second one, and the probability of making your second free throw if you made the, yeah, you know what I mean. The probability of making your second free throw conditional on the first one. These thetas are those two probabilities. And if we look at the actual sample, we see that all the points in our random walk lie on one side of the equality line. If we just looked at this, we could probably guess that they weren't going to be equal for Mr. Griffin. But we also see that this sample is a little bit spotty. It was nowhere near as dense as that really tight circle that I had, even though it was just sort of a play example at the beginning. Generating these takes time because we need to evaluate them against rather complex mathematical formulae that come up in this. And this is why the multi-chain Monte Carlo approach is useful, and this is why IPCluster is useful, because we can generate these dart throws on all of them all at the same time, right? So if we were running this, which hopefully we'll be able to do soon, we would take that script that we ran earlier, and we just ship that script to be run over to the remote nodes. We don't push the actual model object because the communications that happen between your local and your remote namespaces have to be picklable objects, and PyMC models happen not to be picklable. But it's fine, because in this case, all we have to do is ship basically a summary of our data. It was that big lists of zeros and ones that represented the different second free throw outcomes. We ship that data, and then this little script that describes our model, which I'll talk about in detail a little bit later. But it's not very much. We ship a little bit of code, a little bit of data, and then we go ahead and just execute that on our remote nodes. And we can pull those traces back, and the traces being the samples from the posterior probability distribution. And when we go to plot this, we see that these curves are much nicer. They're much more uniform and sort of unimodal, and they look better. It's because we had more samples approximating the actual curves that these are. We see that here. We see that this is a little bit tighter. This probability distribution, there's a little bit less in the tails. The HDI is actually a little closer to 0 here, but it's just because we're getting a better estimate when we have more samples. It still excludes 0. But if we look at the scatter plot of the actual random walk, now we see this is much more dense. And they're in 3 different colors here because we had 3 different nodes calculating these dart throws. And we just pulled all the traces together, jammed them all together, and then we were able to use this as the thing that we did our statistics on. And so it's very beautiful in terms of how parallel it is, and this picture illustrates that. Okay. Kanda? You done? Okay. I think I should probably end here. I really hope you guys run this when you have PyMC working, and we did the basic thing, and we hopefully got something running on on remote nodes, and we got a little bit of output. We learned about blocking and asynchronous calls, and we got a feel for the type of workflow that we're looking for here. I really encourage you to take a look at that notebook. I tried to put a lot of text in there because I had a feeling I wouldn't be able to get through all the details. Read it. Please ask me questions. I love this stuff. I taught math for a number of years. I'd love to talk to anybody who wants to talk about Bayesian statistics with me. Yeah. So are you familiar with just the pickle function? So sometimes there's certain objects that you just can't pickle because they have references to some state on the actual machine that you can't quite encapsulate. Like you can't pickle a file descriptor. Well, you can now, but you didn't used to be able to, and now it just ships some null garbage object. But certain things like that. And for PyMC, it has to do with random states and the fact that you can pause a random walk, and it doesn't want to ship the state of that for some reason. I'm not sure. So the workaround I used, it's just a problem because you can't push that object to the remote namespace. Right. And so what I did was, I didn't quite go through this. I'll talk about it for a moment. When I defined my model, I defined these as lists of these PyMC objects that represented those probability distributions. These are the functions that are the probability distributions, that one picture I showed. And so we've got these PyMC objects, and these PyMC objects are the ones that don't like getting pickled up. But I take those and I assemble them into a PyMC model, and then I run the MCMC command on that, and that's what does the actual sampling, this sample here on the MCMC object. So all I have to do in order to get around it, there's two ways around it. One way was if I packaged all of this up into a class and then shipped the class with all of the state, but it'd be the same thing. My class would just have this script in it. Instead, I chose to use a little bit of magic, the IPython magic. I just saved this block of code with this history command, and I just shipped the code that defined the model over, and I evaled that on the remote. Instead of shipping the object, I shipped the code to create the object.
So if I have my own object that I create in C++ and then wrap it, then all I need to do is make sure that I've got a pickle that's implemented.
Yeah, and I could totally write a better pickler for this. Honestly, I just started using PyMC. It was the last thing keeping me using R was my Bayesian stuff, so I just switched to PyMC. So haven't had time to write a custom pickler for it, but I probably will. It's pretty neat. Okay. All right. Gonna do some MapReduce.
PyMC is actually should be on the car nodes now, master. Under one environment, under the NumPy 1.7, Python 2.7 environment, those should now have PyMC. But not the cluster nodes.
Interesting. Okay. We'll see how that goes. We just left off with IPCluster, and hopefully you learned that that you really shouldn't use IPCluster to push data to those nodes, right? That can be rather expensive. That really you should only push code to where that data already lives. Really, if you're solving that problem, you essentially are recreating the work that MapReduce is already built to solve. Why does it do that? All right. So MapReduce often gets wrapped up in this story about big data, right? I prefer large data. Really, large data doesn't have this whole hype engine around it. And actually, I like C. Titus Brown's comment, data of unusual size. So if you're a fan of Princess Bride, hopefully you appreciate that too, because he definitely does. But it's large relative to what, right? We need to know why we use MapReduce versus something else, right? So if you use Excel, and you can't fit the data into Excel, and hopefully nobody's limited in this case. The only way to solve your problem is to sort of increase the amount of memory that you have, right? That's the only way to do an analysis with Excel is to, and you can't, is to just get more memory. So you have to wait for hardware to improve. And if you're a little bit more advanced, maybe use R, and you're trying to do some analysis that has a lot of, that has maybe like 5 gigs of data and you can't load that into memory, or it's 16 gigs and you have a really big machine. The only way to make R work on that data is to increase memory, right? And the same thing with, if you're doing really low-level stuff, if you're doing C or something like that, and you can't fit it all into memory, the only thing that you can do is increase the memory. So as your data gets bigger and bigger and bigger, you either can wait for memory, or you can go to sort of one of these other solutions that exist. And this is where sort of MapReduce comes in. Really, the power of MapReduce is sort of storing data on multiple disks, right? We have data that's so large it can't fit on a single node, and we now need to go to a distributed file system. So whether you're using Hadoop, whether you're using Disco, the underlying elements of those things are really the distributed file system. It's HDFS and DDFS. And then it's the job scheduler that takes care of, oh, this data lives over here and this data lives over here. So that's really sort of the power of MapReduce. But the algorithm itself is actually it's not so complicated. You have a list of records, or you have a mass of data, and you send each record to a mapper, and that mapper assigns a key to whatever that line of data is. If it's a log file, it might just be whatever that line in the log file is, or if you have a bunch of binary data, you might key off of some element in the binary data, and then you assign it a value. And in this case, the value could be any number of things, but the main point is that all the keys of the same kind get put into the same bucket, and all those buckets get operated on the same reducer. So you're pushing code to where the data is, not pushing data to where the code is. Typically, if it's string data, if it really is just a line from a record file, then often what the key is just a hash of that line, of that text. But in other situations, there might be some more appropriate ways to partition your data. So if you're doing chromosomal analysis, you might partition off the number of chromosomes. So there's some ways of tweaking and fine-tuning that partitioning function. But that's sort of some more advanced features. Yeah, so the typical workflow sort of looks like this. You have your data, gets split up amongst all these mappers. Those mappers take care of assigning these key value pairs to that data, and that code is then pushed to where that data also is replicated on other nodes. But again, the point is that the same key, all the keys are collected together and operated on together. So you have you're guaranteed uniqueness. Now, if you also notice, there's a lot of network traffic. So sometimes there can be some inefficiencies depending on what steps you put on the mapper and what steps you put in the reducer. But if you're more familiar with, again, because SQL is sort of like the basis of a lot of sort of data, or it used to be the basis of a lot of data analysis, maps can be thought of as group bys, and reduces are sort of like aggregation steps. So we're at Continuum, we're sort of focusing on 2 implementations, although right now we're just gonna look at Disco. But Hadoop is arguably the largest MapReduce implementation that exists. It's written in Java. You can get access past the Java with Python through Dumbo or Mr. Job or Hadoop. But Disco is actually really nice. The entire thing is written in pure Python and Erlang for communication. So the distributed file system for Disco is actually quite novel. It's this tag-based system. So it's not like a file system on your directory. It's not a hierarchical file system. You have data that is assigned a tag, and as you push data to this distributed file system, you give it whatever tag you want. So if it's, again, log files are sort of like one of the canonical examples. You might assign a particular log file that date, and then you might want to group all the log files in a month by a single tag and call it, June. So you can tag your tags. And this way, it's like somewhat analogous to just providing symlinks to some hierarchical structure. But in this case, like the tagging system actually works out quite well. It lets me think about the data not as like I have to organize it as June 6th in this folder, in this directory, and then keep on maintaining this very clean structure, I can just sort of tag whatever I want. So MapReduce, it's a party. So batteries are included, just like Python. You can, from your mappers and reducers, you can include the full stack of the scientific Python stack or anything that exists in as any Python library. You can write your own library and include it in a map function or a reduce function. So if you're doing sort of large-scale machine learning or any kinds, anything that requires SciPy or OpenCV or anything like that, you get full access to it. There's no reduced version of Python. And the canonical example of the hello world of MapReduce is count words, and it's not a very fun example, but we sort of have to go through it because it's the hello world. So you should all have a file in your clone called disco_words.py, and it'll look very similar to this. And in gray, I've highlighted the map function and the reduce function. So I have these 3 text files that just live locally in this example. In yours, you're going to be downloading a Chekhov text from the Disco website. And the map function, what we want to do is count the number of unique words that exist in the file. So how many thes, how many a's, how many Sherlocks, how many Poirots. And we're going to key off of that word and assign it the value 1. So the reason that we do that is because all of the keys, again, are going to go into the same bucket. So all the thes are going to go into the bucket, and all the Sherlocks are going to go into the Sherlock bucket. And in my reduce function, where I operate on these buckets, I sort and group the keys. And for each word, I just sum all of the ones. So I sum all the thes, I sum all the Sherlocks, and I'm done. This reduce function finishes, and I just print this out at the end. So let's try running this. So hopefully this will work on several of the Wakari instances. I don't know that there's enough time to debug everybody's, but for those that do work, maybe you could share with your neighbor for those that don't. So I'm going to log out of this. Yeah, I'll show you how to. That's a good question. If you bring up a shell, yeah, just from the shell and navigate. Oh yeah, the editor. So then you're in editor mode. But if you just bring up open a shell, it's just like a shell on your local machine. And just run it from there. Grab it actually. Alternatively, you could run it through IPython if you used %run. What? It's one of the magics of, or no, it's not a magic. What is the %? It's like, is it a magic? Yeah, I guess. Yeah, right. Yeah, that is a magic. Sorry, it's not a bang. It tells it to execute. So it's in exercises and.
Well, I think what it is if you type run, it does an IPython magic command, but you might have a variable called run. So %run will always work.
Okay, so I have this little my script running. If we want to look at what it, it's a bunch of data. Okay, so when I run this function, it executes on these three M1 smalls that are connected to my Wakari instance. It goes through a map phase and a reduce phase. And we can minimize this output, but I thought it would be sort of educational. You know what? I'll just do it from my local machine.
So somehow splitting the work over the three nodes.
Yeah, that's right.
What is being split?
Hold on, let me get this up and running. Okay. There we go. Okay, great. Okay, so has anybody successfully got this working besides me?
I did.
Okay. So some people.
It runs, but then should it be in the output in alphabetical order?
No, it doesn't put it in alphabetical order. It's just putting it in whatever order it came back in. I mean, we can tell it to put it in. Okay, so your question is, what is actually being distributed? So we're actually, so our input file, so everybody should maybe look here. We have only one input file. So only one mapper is actually, only one node in our 3-node cluster is going to download this file. And we only can get one mapper worth of parallelism from this. If we were operating on multiple files or multiple tags, then we'd be able to get some amount of parallelism. But because there's only one file that's being downloaded, we can only assign it to one mapper. And then within this mapper, every word in the file is being split. Every line in the file is being split. And then for every word, I just do a little bit of cleanup. We yield the key, which is the word, and the value 1. So now we have, however many unique words are in Chekhov, right? So let's say there's 200,000 words, right? Or 200,000 unique words. There's probably not that many, right? There's probably like only, like 50,000 or 100,000 unique words. And all those words get partitioned into a bucket, and that partition function is a hash of the string, or the hash of the word, modulo the number of clusters. So we try and get even coverage among the 3 reducers that we have, the 3 nodes. Are you following along? Somewhat? Okay. And each of those nodes is then going to operate on all the buckets that have been collected onto that node. So we've got some amount of parallelism in that we've spread the amount of counting of the words on 3 separate machines. If you ran this locally, this would run significantly faster. This is not actually getting maximum parallelism. Do you have a question? Yeah.
Shipping the data from the map to the reducers, is it pickle or is it just raw strings?
Well, there's no data that's being shipped, right? We're only pushing code to these places.
So how does the data get from the mapper to the reducer?
The data doesn't. The job scheduler knows where the data is.
I'm sorry, your keys and values is what I mean.
Oh, the keys and values. Yeah, these things are going to be written to the DDFS file system, and those will be accessed through either through URLs or something like that. Yeah.
I guess what I'm not understanding is what MapReduce is. I mean, what the idea is.
Well, the idea is that if you have so much data that you can't store it on a single disk, or you had, let's say you had like 510 gigabyte files, and you needed to count how many times something occurred. How would you do that? Would you put the data on every single, you could replicate the data on every single machine, and then you could write an IP cluster function that would say, okay, go to this node has file 1, this node has file 2, And the maximum amount of parallelism that you would get is however many number of files, you'd have that many number of nodes, right? So you'd have to so you operate on each file, on each node, and then the results are returned. But that's a manual process. You have to tell the data to move to that location. MapReduce handles all of that for you. So you push data into DDFS, into this distributed file system. There's some amount of replication that happens. And then there's some internal magic. I mean, it's the job scheduler. And so basically, I view it as, I'm glad somebody else is taking care of that for me. I don't have to worry about figuring out the optimal way of making this data exist for this piece of code. So it takes what could have been a manual process into an automatic one. That's the general idea. So maybe let's keep going, and we'll do something a little bit more significant. So Bitly data is pretty fun. Bitly is the URL shortening service that's quite popular. And a few years ago, they made public all suffixes that were shortened with their service that end in .gov or .mil. The data that exists is typical clickstream data that you'd expect. It's JSON encoded, but in these clickstream data, you'd have the full URL, the shortened URL, where the click came from, whether it was Facebook or Twitter or somewhere else, possible geolocation of where it was clicked on, the OS and the browser. There's a whole bunch of information that's going to be encoded in a single click, and all that's made public. And again, a thank you to Wes McKinney, who actually made me aware of it in his book. Python for Data Analysis is where I first saw the data set. And it's been kind of it's a really good place to kind of get your feet wet with MapReduce, because it's not so large that you can't run data. You can run jobs in a reasonable amount of time, but it sort of has a little bit more leanings towards the kinds of operations and the kinds of jobs that you would do than, say, hello count words. So I've preloaded all of the all of the clusters with, I've pushed a bunch of data to the clusters already. So in the way that you can type ls to look at your local file system, you can type ddfs to look at what's on the distributed file system. So here I have, and this is going to return all the tags that exist on your file system, or on this distributed file system. So I have a day's worth of Bitly links, another day's worth of Bitly links. I've tagged both of these things, calling it Bitly all, and I have some other data on there too. So one thing you might ask is, like a very typical thing, like the most obvious thing that I could think of to ask is, well, what are the top 10 links, right, for that given day? So if we open top 10 Bitly, I included a little bit about what that JSON file sort of has in there, and maybe we should go through this a little bit. So our map function, what do we want to key off of if we want to count the top 10 links? We want to key off of the link, right? We want all of the links to be in the same bucket together. In this case, I'm not really doing any amount of filtering, so I'm just really keying off whatever that link is. Notice, again, another sort of data processing problem. You run into these encoding issues. Sometimes people encode a non-UTF-8. I mean, there's links out there that don't, that are not in there's some UTF-8 issues that are always troublesome. And then I just passed the entire record, so I could actually do a little bit better. I don't really have to ship all that data, as you were saying before. I don't have to push all that data back to DDFS if I didn't want to. But I didn't know exactly what I was doing when I first wrote this script. And then in my reduce function, I have some NumPy lines that let me count up the number of links that exist. And then I'm also storing the latitude and longitude, because I thought, oh, maybe I would want to do some GIS introspection later on to see where those links were coming from. So again, I key off of the link, and in my reduce, I have the link here and the record. So I go through the entire bucket and I count the the number of links that exist. I just add one every time that that particular link appears. And then I sort that entire dictionary, and I have I take the top 10 of them, and then I return it. So every reducer, so I have 3 reducers in this case, and everybody else has 3 reducers, have a top 10 of them. So I have to do it one more time on the local node, right? So from my reduce, I have 3 sets of top 10. Then I need to take the top 10 of the top 10 of the top 10. So I do it one more time over here. And then below, I just have some nice sort of plotting functions to let us look at it. So why don't we run that? Can everybody try it and run that?
But that doesn't necessarily get you the top 10 global.
That gets me the global top 10 of the day for all links that have a suffix of .mil or .gov.
I mean, the top 10 of the 3 top 10 is not necessarily the top 10 for the whole set.
It should be. So if I have a list of 3,000 numbers randomly assorted, and I chop it into 1,000 bits each, and I ask for the top 10 of the first third, the top 10 of the second third, and the top 10 of the last third, then I can take the top 10 of all those things, then I'll have the top 10 of the global space. Regardless of how I distribute it. This. Yeah, so I ran this. You get 9. Oh, so it's the top 9. Okay, it's the top 9. Great. Okay, I can help you after. So the nodes will be up for a little bit longer, but just for the sake of time. So maybe we should. So I ran this thing and this. I just ran it against a tag, right? Maybe we should look at that script one more time. So here, instead of one of the nice things about Disco, is that I can include a URL or a tag or a local file or a raw bit as my input. Hadoop is a little bit difficult to do that, but that's one of the things I really appreciate about Disco. And this tag is actually tagging all the files, right? So why don't we look at? It's not just a single file, so I'm actually getting some amount of parallelism. So we can look at all the blobs that I've pushed up. So if you look at DDFS blobs and then just this, I should get a huge list of files. So there's a ton of files there, and actually I've told all my nodes to have a replication factor of 3. So I'm guaranteed that every single all data exists on each node. So I get maximum parallelism. Oftentimes this is not actually tenable, but in this case it's essentially like I handed however many unique files there are. I handed that to the mapper, essentially a list of all these files. So mapper 1 gets 1 file, mapper 2 gets 1 file, mapper 3 gets 1 file. It operates on it, and then it gets another set of files. Mapper 1 gets another file, mapper 2 gets another file, mapper 3 gets another file, and it keeps on going until I've exhausted the list of input files. But I didn't have to specify that list. I just included that one tag. So
Why is it 9?
because I didn't code it up with 10. I accidentally coded it up with 9.
Where is that in the code? It looks like you put 10, right?
Yes, I'm excluding the last record there. So when you run this, it will actually produce all these images and a bunch of output, right? So you need to get an image viewer.
Just cat a PNG.
Can I?
Sorry.
Great. Oh, I can just look at it. So this is what one link looks like. This particular link comes from dpi.wisconsin.gov. Yeah. So in doing this kind of, when you look at clickstream data, you can sort of see how people are, viewing, how people are viewing links. Like, do they look at it in the morning? Do they look at it later at night? Does it have, in this case, it's bimodal, but maybe, for this one, it's not, right? This particular link, for some reason, was popular. It decayed a little bit. It got a resurgence. And then all of a sudden, it greatly accelerated. So I'm just doing cat and then the file name. Here's a NASA, NASA.gov is really popular. They share a lot of images that get spread throughout the, every time NASA puts up a picture of the day, that's pretty popular everywhere. But this one has sort of a more regular pattern that you'd expect. It gets shared and clicked on a ton, and then all of a sudden nobody cares about it later in the day. So you can try and maybe characterize, does NASA do a better job of, getting data, getting URLs clicked on than NIH? Which government oversight committee is better at spreading the word about their latest, document or something like that? So it's quite fun. This is only data that's been encoded by Bitly. Yeah. If they click the direct link, you won't have this. But this is the kind of stuff that, I guess, Bitly is interested in doing these kind of analysis. They want to know, over time how people are sharing data and how it's sort of flowing through the internet. The reason that I actually copied that I had those geolocation images is because you see a lot of those, like the progression of viewing links over time. So I decided I just wanted to make a little movie of, of what that looked like. So you see a ton of data over in the East Coast, some in the West Coast, not so much in the middle. I'll run it again. So this was a day's worth of Bitly data. There's a lot in Western Europe, some in India. If we slowed this down a little bit more, you'd see very expected human behavior. At least in the U.S., you'd see the East Coast come online, and then people. Those things are quite popular to do. So, you see the East Coast come online, the Midwest, and then pushing over to the East Coast. It's in the bundle, right?
It was in the directory.
Oh, yeah, there it is. Oh. You wouldn't do it? Yeah. Okay. Yeah.
It'll cat more stuff than you think it will. But yeah, I guess.
Okay. Yeah. So that data is a lot of fun to play with. I encourage you to play with it on your own time. And then some other questions that you might want to think about in terms of just general questions about Clickstream or about NASA is who's more popular. Do most people look at links on mobile devices or on regular devices? These are sort of like things that you might think are actionable. Maybe they are. If you did the analysis. if a ton of people are looking at your site on Nexus and iPad, stuff like that, you might want to optimize your site for those kinds of things.
Can I ask a question later about how that top 10 of the top 10 works? Because if I can understand how that works, then I can understand how MapReduce works. I think I've written down an example where it won't work. And so if I can understand why my example can't ever happen, then I'll understand MapReduce.
Okay, maybe we could talk after this, and we could go into detail. Is that okay? Okay. I mean, okay. I mean, so if I take, so
There's going to be some problems that MapReduce won't, but I'd like to see your example, because for this one, it seems like it's going to work. I'm not able to think of an example where it wouldn't on this particular
Well,
one.
I'm making an assumption. I don't know whether the assumption is right or wrong, and it has to do with how MapReduce works, I think.
Well, I mean, forgetting MapReduce, if you just had, you were just counting stuff and you wanted to know what the largest number is, and you just split it into 3 from the largest 10 numbers.
You've got a pile of objects, right? And and in that pile of objects, you've got sub to that some number of identical objects. So you're making a histogram of those objects. But before you do that, you split that pile randomly into 3 lumps and count each of them separately.
Partitioning is
What
what's
you're going to
making
wind
this
up
impossible.
doing is you're going to wind up with 3 histograms you really have to add together in order to get your top 10. You just take the top 10 for each of those 3 histograms.
but you're not
Necessarily going to get.
making histograms. You're not.
I think he's giving motivation for the reduce.
Right.
Yeah.
This is a MapReduce reduce is what he did.
So you described the match step, I think, quite well.
Yeah.
The notion of needing to combine those histograms, because once the original data was split into 3 separate, who knows how they were split up randomly, because it's almost meaningless to the histogram. You need to be able to consolidate, and that is what the reduce step is for, is to do that consolidation.
Okay, so why are we doing it twice?
Then maybe if you, I don't know where you are in terms of
We can-
solve, but would it be possible to jump to that code in particular to take us through exactly that?
Sure. So we've already assumed that we've issued out all these links. So we have all links are going to be spread out amongst 3 nodes, right? But we are guaranteed that link A is going to be in the same bucket, and link B is going to be in the same bucket, right?
I think that's where you're having the issue. If they're not randomly distributed into 3 buckets, all the links which are the same are in the same bucket.
Oh, okay. And that's a common feature of MapReduce, or that's?
Yeah, you have to. The idea of that's I think the part that you're having trouble with is that all the keys of the same keys get put into the same bucket, and you're guaranteed that. Otherwise, you would have that problem of not being able to do basically anything if you didn't have uniqueness.
And you can't do that in parallel.
You can't do what in parallel?
Sort across the entire set of data.
You have
Put them all
to
into the same bucket. Sort everything so that they're neighbors. That sort operation is something that you're correct in that if you had a list of words and a words example to back up to that one, they're talking words and words. If you want to count, then not having to create a ginormous dictionary, but we can just keep all of the words that are the same word next to it. Sort them all first, and that's something that you can't necessarily, you can, but easily do a distributed sort. So there's the, right, sorted as being invoked in there, inside of the reduce at that step, but also is the sort being invoked before the reduce step in this one?
No, I'm just putting out all the words.
It's just there, so, but
So this just prints out, this will print out the unique words and the number of counts, but it won't sort them in terms of the number of counts or the alphabetical sort.
I guess what I was hoping on is maybe not the clearest example, but the notion of doing a sort across all of your data, that's not necessarily something that's easy to do parallel. And that's something that may motivate you to reorganize the way that you break down the problem to avoid that mistake that you make.
This is what partitions mean. So while I can't sort, like by partition, all those keys are, so the words are hashed. That object is a hash table, right? The object that's output by the mapper in the word count example, because that's the most easiest to think of, it's a word and the number 1. That word is hashed because that's an object in a hash table. I don't need to sort. I just divide up my hash space. Say, all right, you know, a third of my hash space goes here, a third of my hash space goes here, a third of my hash space goes here. That way I guarantee all of the zebras are together and all of the apples are together. They may be next to each other in hash space, but I know that they're at least together on the same node,
basically,
chopped up together.
I'm understanding what you're saying, that when you do the reduce function, when it goes out between nodes, it's not the same set as three files in the map.
That's right.
Right. So if we,
and at that
yes.
point, when you do the reduce, everything's going uniquely based on the unique hashes.
That's why these arrows are going every which way
Yeah.
here, is because
So
they're
this is-
getting assigned to buckets based on their hash.
So here's the hash of all these words. The hash of this word modulo the number of, in this case, modulo 4. This should be modulo 5, but. So all the ofs go to bucket 5 and go to reducer 5. And all of the courses go to 0. So we take the hash of every single word. They go into all the unique buckets that exist, modulo the number of reducers. Yes?
So in this example, the like reading of the words is done on one CPU. So what goes out is the like.
The only reason that it's done on one CPU is because I only gave it one file. If I had chunked my file up into, if I had like split the file into thirds, then I'd be able to get some more parallelism.
Right.
But
So
okay.
so if you did that, then you'd have to combine them to know.
It doesn't matter that the idea is that, again, it's an embarrassingly parallel job because it doesn't matter that a third of the file being done on map 1 is the third of the job being done on map 1 will be the same as the job on map 2. The hash function of on map 1 will be the same value as the hash function on map 2 of.
And you can split hash space into thirds without looking at where the data is. If you're working on big enough data, your data is going to be uniformly distributed across hash space.
But where in the code does it say that you only do it on one machine?
Where in the code does it what?
Does it say that you're only using one machine for one of the bits and three machines for the other three pools or whatever?
Well, there's this thing right here that says partitions equal 3. But because I only gave it one file, I don't need 3 mappers to download one file. I only can download one file from one node. If this,
But
it's right here. It's implied. There's only one file listed right here.
There's one input, which is a string, so there's only one mapper that.
If you gave it 6 inputs, then it would run the three. It's just the way that this jump class works.
I think that holds no matter what MapReduce framework we use. Mappers are determined by the number of inputs that those are the mappers you get. How many reducers you get is something that you can control, and that's what the partitions is controlling for us. So we determine the number of mappers by the number of inputs.
But if you say that the input there is list, you just gotta have
But that's exactly why it's expressed as a list.
So suppose we split the check-off into 3 parts.
Okay.
Put those 3 there.
Why don't we do that?
Get string mappers started.
Right. So then we have 3 independent hash tables with 3 different machines. Now we have to combine them.
They all
No, you don't have 3 independent hash tables.
hash function's the same.
The hash function's the same. type on, load an IPython up here. That's the hash regardless of wherever you run it. I mean, for this compute node, that will be the same on all the compute nodes. The hash of that string will be the same everywhere. So it will appear in the same bucket no matter what. So all of the, but it doesn't, you don't have counts. You just have the key and the number 1. Okay, well, okay. Well, I think we're out of time. There's some other things. Maybe we could just sort of wrap up with some thoughts about MapReduce. So generally, I use MapReduce just as a filtering thing. Trying to do numerics with it can be dangerous, although it can be done. But it's really, everybody's pain point is data cleansing. MapReduce is really effective at being able to just filter out a lot of data. In the same way that SQL was designed to sort of do a lot of group bys and filterings, when you have data that doesn't fit into an SQL table, MapReduce is sort of here to save the day. And that task deconstruction of saying this job is part of the mapper, and this other piece of code is part of the reducer, it's nice to have your code split up like that in terms of readability and in terms of just job decomposition. But there can be a lot of network traffic, so you should be mindful of those things. And this is the last 2 slides, I promise. So are there any neuroscientists in the room? Neurobiologists? Do you see a problem with that picture? Does anybody see a problem with this picture? It's upside down. Okay, so there's neuroscientists like to play with gorillas a lot. There's this thing called inattentional blindness. And a bunch of research was done into this. So you show this picture to a bunch of neuroscientists and you ask them, do you see anything wrong with it? The idea is that they miss this gorilla. And if they're missing this gorilla, what else are they missing, right? They're missing all the tumors and everything like that. So 83% of radiologists miss the gorilla, right? So we can't we're sort of like bound by ourselves. We're flies in the fly bottle. We can't get out of it. And our first thought is, we'll just train computers to figure out, we'll train every single neuroblastoma into a classifier. We'll be able to machine learn our way out of this problem. So on the opposite end, you have Google Flu, which for a very long time was able to provide really good statistics on how bad the flu outbreak was going to be. So if you get sick, before you see the doctor, if you see the doctor, you immediately go onto Google and type, do I feed a fever, feed a cold? Do I, what are common herbs that I can take to make my life any better? And Google internalizes those things and does some analytics and was able to predict with high degree of accuracy how bad the flu outbreak could be. Because those statistics those metrics are actually recorded sort of live. The only way the CDC gets those metrics is if you go to the doctor, you confirm that you have the flu, and that data is then reported downstream to the CDC. But in last year, if you recall, the flu outbreak was supposed to be significantly worse than it was, right? So Google got it totally wrong. They predicted that we were going to have this terrible thing because we had this sort of like this hype engine around, the flu outbreak is going to be bad, the flu outbreak is going to be bad. Everybody sort of essentially became a scale-free network and was like constantly searching what's going on, and that destroyed Google's machine learning algorithm. Now, there's definitely ways to account for those kinds of things. Google probably could have done it, but whichever team of engineers or single engineer just coded it up, let it run, and then you had this problem. Now, there's not a lot of major problems with this, but the take-home point is we have inattentional blindness that we can't escape. And we have machine turnkey analytics, on the other hand, will lead us to a path, that is not built with accurate predictions. So you have to be careful and find this middle ground between, human input and machine learning. And those two things probably will always coexist together. Thanks for coming out, and thank you to the SciPy organizers.